Hello there, this is an Algebra 2 video. It is Chapter 5, Section 7, and today's topic is roots and zeros. And before we begin, I want you to pay attention to what I have on the board here. These are basically 4 different statements that are all equivalent in the world of algebra, and especially when it comes to roots and zeros. So a lot of times you hear the statement like find the zero, or find the root, or find the solution, or factor, and all these things. And sometimes we get to thinking that they're all different elements of the equation, and they're not. So I want to make sure that you understand these equivalent statements, that saying that C is a zero of P of X, like if I say 5 is a zero of P of X, it's the same thing as saying that 5 is a root or a solution of the equation, the polynomial equal to 0. Also, that when you say if 5 is a root or a solution, then it's the same thing as saying that x minus 5 is a factor of the polynomial. Another way of looking at solutions and roots and zeros also is as x-intercepts. That's my last statement here, that if 5 is a 0, then 5 is also an x-intercept. So c comma 0 is an x-intercept of the graph of the polynomial. These are all just equivalent statements, so that when you hear them, you understand that they're all asking for the same, pretty much the same thing. So today we have the fundamental theorem of algebra, and it's pretty fundamental to algebra. And it says that every polynomial with degree greater than 0 has at least one root in the set of complex numbers. So we know that in the previous chapters, we already talked about complex numbers and the imaginary unit I. And so at this point, everything under the sun is considered complex. Even numbers that you wouldn't normally think of as complex could be considered complex. I just want to give you an example real quick. For example, I don't think anyone would think of the number 3 as a complex number, but the point is that it is part of the complex number system, because the complex number system includes all numbers that have both real parts and imaginary parts. So things like 3 plus 2i definitely qualify for a complex number, because you can see the imaginary part right away. But a lot of times when you see just the real part, you think that it's not an imaginary number, or that it's not a complex number. And it can be, because you can write that as 3 plus 0i, and then it would qualify as a complex number. So basically, back in the day, we did our little Venn diagram, and we know that you start off with counting numbers, the natural numbers, and then that includes 1, 2, 3, 4, 5, the numbers that you use to count with. And then after that, you have your whole numbers, which is basically all the natural numbers, including 0. And then you have, after that, your integers, which introduces all of the negative numbers as well. So now you've got -5, -4, -3, 0, 1, 2, 3. And then you have the rationals, and that's where things start getting really fun. Rational starts including all the fractions, all the decimals that no one likes to deal with all the time. And then you have your rational. And that's kind of where things get kind of divisive. In fact, instead of a circle, we'll use a square for the rational part, because then you have another square over here that is for the irrational part. And there's no overlap. So you kind of understand that if you're a rational number, then you're automatically, if you're a natural number, because the n is inside of the box of the r, the natural number is automatically going to be considered rational. So again, rational, basically all the numbers that can be written as fractions. So things like 1/3, 2/3, all the decimals that go on forever, but as long as you can write it as a fraction. Over here you have things that can't be written as fractions, decimals that have no pattern. But the point is that there's no overlap. However, at the end of the day, everything is considered to be in this big black box, which is the real box, which means all the numbers here, whether they're rational or irrational, are real. And of course, way off to the side, you have another box, and that's where the imaginaries are. Okay, so now what we're basically saying with this whole fundamental theorem of algebra is that now everything is considered, let's go back. Uh-oh. Let me see. Sorry there, people. There it is. I hit the wrong button over here on accident. Anywho, so we have now, this is the world of complex. And a complex number is any number that has a real part and an imaginary part. So any number in this, all of these numbers are going to fall under the umbrella of complex. So everything under the sun is complex now. So that being said, when we read the fundamental theorem of algebra, it's saying that every polynomial with degree greater than 0 has at least one root in the set of complex numbers. But of course it does, because if every polynomial greater than 0 is going to have a root, and since the only numbers that exist in the world are complex, it's going to have to be in this set. So that's basically what it's saying in a nutshell. Now for us, for the purpose of what we're doing in our homework today, it's more important for us to understand the corollary, which we will get to after this example. But for now it says, solve each equation, state the number and type of roots. So we know how to solve this little guy. We tried the factoring method, and I say 3 times 3 is positive 9, and 3 plus 3 is 6. So since both of these factors are the same, I get x plus 3 squared equals 0, or basically x plus 3 equals 0 twice, and x equals negative 3. That's my solution. So state the number and type of roots. The number of roots is 2, and this number is going to be rational. So basically this is what we call a repeated. We have one repeated root because we got the same thing twice. When you see x plus 3 squared equals 0, it's basically saying x plus 3 times x plus 3, and we already know that when you have the two factors, you make each one separately equal 0. But in this case, I only had to do it once because they're both going to give me the same result. So in that case, you have what they call a repeated root. So you have one real repeated root, which is negative 3. Sometimes we refer to that as a double root. But there we go. So over here, we're going to factor out the x and get x squared plus 25 equals 0. So now I know that either x equals 0 or x squared plus 25 equals 0. So this time, my factors aren't the same. So I have two separate problems to do. So there's one of my zeros, or one of my roots, one of my solutions. And over here, I'm going to continue, and I'm going to get x equal to plus or minus 5i. So now you want to state the numbers. So we have 3 roots, but one of them is real because the 0 is a real root, and the other one is imaginary. So you have 2 complex. And that's just stemming from the previous lesson where we talked about real versus complex roots. Alrighty? So that is how you determine your number and type of root. So now we're going to let you attempt this little guy, and then we'll go on to the corollary that I was talking about earlier, which is probably the part that's going to be more important for us, is the corollary to the fundamental theorem of algebra. So I abbreviated the fundamental theorem of algebra. I don't want to write it all out. But a corollary, if you remember from geometry, is basically a one-step proof that basically almost directly follows the previous theorem. So the fundamental theorem of algebra is a theorem, and based on that theorem, we have this corollary, which is a very easy progression from the previous theorem. And this is the one that's probably more applicable to us. A polynomial equation of degree n has exactly n roots in the set of complex numbers, including repeated roots. Now again, that might sound really fancy, but basically what it's saying is that any polynomial of degree n is going to have n roots. So once you take into account any repeated zeros or any repeated roots like we did in the previous one, then when you look at, so basically for example, when you look at x squared, this is a polynomial of degree 2, the exponent here is 2. degree 2, so we should expect to have 2 roots. But that includes repeated roots. So even though in this case we only got 1 root, it was repeated. That means that it counts as 2. It's 1 root that counts as 2, so therefore x squared is n equals 2, and there's 2 roots. Over here you have x cubed, so n equals 3, so you're supposed to have 3 roots, and we do. We have the 0, the positive 5i, and the negative 5i. So once you include complex and all the repeated roots, then that's what the corollary to the fundamental theory of algebra is telling us, is that depending on the degree of the exponent, of the degree of the polynomial, that's how many roots it's going to have. Now that being said, we have Descartes' rule of signs, and Descartes is a famous mathematician who came up with this, observed this relationship among polynomials on how to determine. We know that they're going to have, like if I have x to the 5th power, I know it's going to have 5 roots, but what I don't know is how many of those roots are going to be positive or negative. And so Descartes put together a little, a formula, if you will, for us to determine whether or not it would be positive or negative. So here we are, Descartes' rule of signs, and it says the number of positive real roots for a polynomial is equal to the number of changes in sign of the polynomial, or less than this by an even number. Okay? What that means is, well actually I'm just going to leave it at that. I'm going to show you with an example in a second. Sign changes are basically how often the terms in the polynomial change from positive to negative. So let's suppose that in one of the polynomials there are 5 sign changes. It changes from positive to negative 5 times. If that happens, what Descartes noticed is that the number of positive real zeros is going to be equal to 5, or it's going to be less than 5 by an even number. So that would mean that there's either going to be 5 positive zeros, or 3 positive zeros, or 2 positive zeros, or no positive zeros. Because you start with the 5, so it's either equal to the number of sign changes, either equal to 5, or less than 5 by an even number. So you can't have 4, because 4 is not less than 5 by an even number. 4 is less than 5 by 1, and 1 is not an even number. 3 is less than 5 by 2, and 2 is an even number. 2 is less than 5, and so, but actually 2 doesn't work either. I'm sorry, I should have made that a 1. I just caught my own mistake, see? Lovely. 1, so 2 doesn't work because 2 is less than 5, but 2 is less than 5 by 3, and 3 is not an even number. But 1 is less than 5 by 4, and 4 is an even number. So either, if you have 5 sign changes in the polynomial, then either there's going to be 5 positive zeros, 3 positive zeros, or 1 positive zero. Obviously you can't go to -1 because then it makes no sense to have negative zeros. But anyway, so then it also has a part for negative zeros. The number of negative real zeros is also equal to the number of changes in sign, but this time you're going to plug in a negative x into the polynomial. But again, it has the same, aside from plugging in negative x versus regular x in these two scenarios, it's pretty much the same. Either it's going to be equal to that, so again, if I plug in negative x into my polynomial and I get 3 sign changes, then the number of negative real zeros is going to equal 3, or it's going to be less than 3 by an even number, so 3 or 1. And that's it, okay? So now, perhaps you're probably still going, what? And I'm going to show you with this example how this works. So state the possible number of positive real zeros, negative real zeros, and imaginary zeros for f of x equals, and we have this big old long polynomial. So the first thing we have to do is identify the sign changes. Okay, where does the sign change? So what I mean by that is this is a positive x to the 6th, and this is a positive 3x to the 5th. That is not a sign change because both terms are positive. But positive 3x to the 5th minus 4x to the 4th, there you have one sign change. It went from positive to negative. Then you have negative to negative. There's no sign change there. Negative to positive, there's a sign change. Positive to negative is another sign change. And negative to positive, again, is another sign change. So we have 1, 2, 3, 4 sign changes in this example. So for the positive, the possible number of positive zeros is going to be equal to the number of sign changes, which is 4, or less than 4 by an even number. So it's going to be 4, 2, or none. You're going to have either 4 positive zeros, 2 positive zeros, or no positive zeros. So if you have 4 positive zeros, now keep this in mind, you have x to the 6th power here. This tells us that you're going to have 6 zeros. And this is telling you that you're going to have 4 positive ones possibly. If you have 4 positive ones, then perhaps the other 2 are negative, or perhaps the other 2 are imaginary. If you have 2 positive zeros, then perhaps the other 4 are negative, or perhaps the other 4 are imaginary. If you have no positives, then perhaps the other 6 are negative, or they're a combination of negative and imaginary. That's kind of what's happening there. So now, that's the first part for positive real zeros. Now for negative real zeros, we have to do a little bit of work for that little guy. We have to find f of negative x, which means we have to plug negative x into all of those x's. Okay, so we're going to go negative x to the 6th power plus 3 times negative x to the 5th power minus 4 times negative x to the 4th power minus 6 times negative x cubed plus negative x squared minus 8 times negative x, and lastly plus 5, running out of space there. And then we have to simplify this. Well, anytime you have a negative raised to an even power, you're going to get positive, because a negative times 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 a negative, 6 negatives together, what's going to happen is each pair of negatives will become positive, because negative times negative is positive. So in this case, when you have 6 negatives, you're going to pair them up into 3, but they're all going to be positive. So anytime you have an exponent that is going to be an even number, this is going to be positive x to the 6th. Now this is an odd number here, so this is going to be negative x to the 5th, so it'll be minus 3x to the 5th. Then we have, this is going to be positive, so it's going to be positive x to the 4th, but that's still a negative 4, so it's negative 4x to the 4th. The negative x cubed and the negative 6 are going to be positive 6x cubed. And then the negative x squared is going to be a positive x squared. And then we have negative 8 times negative x, which is going to be a positive 8x, and then plus 5. So now we're looking at the sign changes. All right, so we went from positive to negative, that's one sign change. Negative to negative doesn't change at all. Negative to positive is another sign change. Positive to positive, positive to positive, positive to positive. So there's no more sign changes. There are only 2 sign changes here. So that means that for the number of negative zeros, you're going to have either 2 or none. So one scenario here is you have 4 positive and 2 negative. Or you could have 2 positive and 2 negative, but then the other 2 would have to be imaginary because there has to be 6. If you have no positives, then you could have 2 negatives, and then the other 4 would have to be imaginary, so that you could have 6. Or they have to be repeated in some way, okay? If you have no positive zeros, I think I already went to that scenario, you could have no negatives. So if you have 4 positive and no negative, that means the other 2 are imaginary. So we've talked about the number of positive zeros and negative, that's Descartes' rule of signs. And so the last part of the question that we need to answer is the imaginary zero situation. So they actually want us to write out all of those scenarios, but I kind of already walked you through them, but I'm going to try and answer the question here. We want to put up on the board also the number of imaginary zeros that are possible. So again, we're going to say that if there's 4 positive and 2 negative, then you don't have any imaginary. If there's 4 positive and no negative, then you have to have 2 imaginary. So that's the first scenario, or the first couple scenarios. Our next scenarios are, what if you have 2 positive, 2 negative, then you would still need to have 2 imaginary to make your 6. If you have 2 positive and no negative, then you would have to have 4 imaginary to make that scenario work. If you have no positive zeros, 2 negative zeros, then you would have to have 4 imaginary. And that's basically the options that you have. So for imaginary zeros, you either have 4 or 2 imaginary zeros. In no scenario can you have no imaginary. So I guess you can, if you have 4 positive, 2 negative, then that would be 6, and then you would have no imaginary. So that is a scenario. So it's possible that you have no imaginary, 2 imaginary, or 4 imaginary based on the scenario. So now you should do it yourself, number 2. So remember that when you do the negative zeros, you have to plug in negative x before you can determine the sign changes. All right. And so now we have example 3, which I believe is our second to the last example. And it wants us to find all the zeros of f of x. Now, because we have x to the 4th, we know that we should actually have 4 zeros. And so the first thing you want to do is determine how many are you going to have. So we're going to have 4 zeros, and that's because of the corollary that we talked about. And how many of those are going to be positive? And how many of those are going to be negative? That's the next question we want to ask. Sign changes for positive, we have 1 sign change, 2 sign change, and then no sign change there. So we have 2 sign changes, so either 2 or none. For the negative zeros, we're going to do this real quick like. I don't want to erase my problem, but okay. We need f of negative x. If I plug in a negative x to an even exponent, it's going to stay positive. This is again a negative x to an even exponent is going to stay positive x squared, but that's negative 18. 12 times negative x is going to be negative 12x, and then plus 80. So in this case, I have positive to negative, that's 1 sign change. Negative to negative doesn't change at all. Negative to positive is another sign change. So again, we have 2 sign changes. So there's either going to be 2 or no negative zeros. So those are my options for the types and number that I'm going to get. So now I'll erase this negative x thing and actually try to solve this guy. And I am going, because there's 4 terms, I'm going to try to factor this by grouping and see if I can get what I need to get out of here. Let's see if I can do this. It might not work, so we'll see. X squared minus 18 plus 12 times. Yep, that's not going to work. So the only thing that I have to do now is division. Division, division, division. Now remember that we're looking for solutions. So with synthetic division, you can find 1x to the 4th, 0x cubed, negative 18x squared, 12x 80. We're looking for a 0 remainder, okay? So I am going to try now trust me, in the next lesson we're going to have a better way of finding some of these zeros, but right now we kind of just have to guess. So what you want to do is have your calculator handy. I'll grab mine. And what you want to do is basically try values, obviously positive values. You basically make a t-table for your function. And remember what we did before, what you're looking for is for your values to change sign. If they change sign, it means that somewhere in between there was a 0. So, for example, I'm going to pick -3, -2, -1, 0, 1, and 2. We're going to put the equation in the calculator. X to the 4th minus 18x squared plus 12x plus 80. All right, so here I'm going to get -37, 0. Ooh, look at that. 51, 0 is 80, 75. Okay, so all I'm doing is I'm putting in some values here, but what I wanted to show you was that when you randomly pick numbers, you have to make your own little t-table. You can see that this is a negative value, this is a positive value, so somewhere in between those there had to have been a 0. Now in this case we got lucky and I actually got a 0 by plugging in -2. But that's just 1, and I have to find 4. But luckily for us, you don't have to get very crazy. Once you find 1, you can use that one to help you find others, because you can get your polynomial to get smaller and smaller. So what I'm going to do is I'm going to go ahead and use synthetic division with the -2 because I know it's going to work. Sorry, wrong number there. Okay, so now this is a cubic. So now I have x cubed minus 2x squared minus 14x plus 40, and I can continue to try to find another 0, perhaps in my table here, because I need to keep finding some more. In my table here, I'm going to keep going over here, negative, what was this, 37? That was -3. I'm going to try -4. As well. Oh, look at that, I got lucky again. -4 is actually also a 0, so now I'm going to divide by -4. Notice that I'm not going to divide the original problem, I'm going to derive what I have, what I was already left with. So 1 times -4 is -4, it's going to be -6, it's going to be positive 24 minus 14 is going to be 10. And 10 times -4 is -40. And so again, now what you can see happened is, the first time I divided, I got a cubic. The second time I divided, because it always goes down by 1 degree, now this is a quadratic. So now this is like x squared minus 6x plus 10. And that's your goal. You always want to get down to a quadratic because we can use the quadratic formula to find the zeros now from here on out. So now we're going to plug that into the quadratic formula. So I'm going to go x equals -b plus or minus radical b squared minus 4ac all divided by 2a. Notice that when I said x equals -b, since b was already negative, it made it into a +6. And then b squared, -6 times -6 is positive 36, minus 4 times 1 times 10. So 6 plus or minus the square root of 4 times 10 is 40, so 36 minus 40 is going to be -4, and that's why we're going to get some imaginary numbers here. 6 plus or minus the square root of 4 is 2, but it's in negative, so it's going to be 2i over 2. And 6 divided by 2 is 3 plus or minus I. So now we have our 4 zeros. We have -2, -4, and then 3 plus or minus I. So we have 4 zeros. And we're supposed to have 4 zeros because we knew this was a 4th degree polynomial. And that is how you do that. And so now we'll let